Okay, in section 4.7, we're going to go back to limits and learn L'Hopital's rule. Sometimes this is spelled, it looks like La Hospital, but you still say L'Hopital's rule. Okay, so we're going back to limits. Okay, so remember when you're evaluating a limit, the first thing is we just try to do direct substitution. So this is the limit as x approaches 3 of 2x minus 5. So we would just plug in 3. So 2 times 3 minus 5 over 3. So 6 minus 5 is 1. So the limit is 1/3. Easy. Okay, now L'Hopital's rule addresses the indeterminate limits where we had to do extra work. So if the limit as x approaches a of some quotient f of x over g of x approaches 0 over 0 or infinity over infinity, which were the indeterminate formats where we had to do extra work to evaluate the limit, then the limit as x approaches a of f of x over g of x is actually the same as the limit as x approaches a. If I take the derivative of the numerator and the derivative of the denominator. Isn't that weird? Okay. We're going to use L'Hopital's rule when possible on these things. Okay, so for this one, if I plugged in 2, the denominator would definitely be 0. If I plug in 2 on the top, I get 4 minus 14 plus 10, which is negative 10 plus 10, which is 0. So this is 0 over 0, which is an indeterminate format. Now in chapter 1, when we solved this, don't write this down. You remember we just factored it? We're like, okay, this is x minus 5, x minus 2. Limit as x approaches 2. We crossed off this, and then we plugged in the 2, and then we would get 2 minus 5, which is negative 3. Okay, now they're telling me that this is another way I can solve that situation where the limit is indeterminate. So I'm going to keep it as the limit as x approaches 2. But I'm going to do the derivative of the numerator and derivative of the denominator. So the derivative of the numerator is 2x minus 7. Derivative of the denominator, x minus 2, is just 1. Okay, now if I plug 2 in now and do direct substitution, I have 2 times 2 minus 7, which also gives me an answer of negative 3. Okay, let's go ahead and look at B and see if we can use L'Hopital here. Okay, 2 minus 2 at the top, definitely 0. Accepted. Okay, what about the bottom? Uh-oh, I don't think I can do that in my head. Okay, 0 over 3 times 8 minus 6 times 2 squared minus 4 plus 2 minus 2. That's 24 minus 24, that's 0, plus 2 minus 2, that is 0 over 0. Because it's 0 over 0, I can apply L'Hopital's rule, and because it's a fraction. Okay, so if I take the derivative of the numerator, I get 1. If I do the derivative of the denominator, I get 9x squared minus 12x plus 1. Okay, and now I can do direct substitution on this. So this is 1 over 9 times 4 minus 12 times 2 plus 1. Those 36 minus 24, 12 plus 1, 1 over 13. Now, if I had tried one of our old strategies like factoring, I would get the same result. But this makes some of these a lot easier. For example, number C. C is 6 times 0 is 0. So the sign of 0 is 0 over 0. We learned an identity to address this. Some of you struggled with that identity. So luckily, we have another way of evaluating it. Since it's a fraction, I can take the limit as x approaches 0. I'm going to do the derivative of the numerator. So the derivative of sine is cosine of 6x, and then because it's 6x, I'm going to use the chain rule. The derivative of 6x is 6, so I'm going to times it by 6. For the denominator, the derivative of x is 1. Okay, let me go ahead and plug this in. So 6 times the cosine of 0 divided by 1, which is, cosine of 0 is 1, so 6 times 1 is 6. And that's the same answer as if we had used the identity we had learned. Okay, let's look at another one. If I plug in 0 here, the cosine of 0 is 1. So I get 1 minus 1 over 0 squared. So that's 0 over 0. It's definitely indeterminate. I can apply L'Hopital. L'Hopital only works when it's 0 over 0 and infinity over infinity. Okay, the derivative of negative 1 minus cosine is 0. Derivative of negative cosine is positive sine x. The derivative of x squared is 2x. Okay, now let's plug in 0. If I plug in 0, sine of 0 is 0. 2 times 0, oh, I still have 0 over 0. Okay, well, let's apply L'Hopital's again. Okay, now let's do the derivative of the numerator again. So derivative of sine is cosine. Derivative of 2x is just 2. Now, will this work? The cosine of 0 is not 0. The cosine of 0 is 1 over 2. Okay, and then hold on because I'm going to change this. Okay, last one. We're going to do one with infinity. Okay, if I do 2 times infinity squared, I get some kind of infinity. E to the 2 times infinity, I get some kind of infinity again. And we kind of reasoned our way to the answer with these, but now that we know L'Hopital, if you get infinity over infinity, we can apply L'Hopital's rule. So let's do the derivative of each. What am I going to get? I'm going to get 4x over derivative of e to the 2x is e to the 2x, and then chain rule times the 2. Okay, let me cancel out the 2 just to make it easier for me to stare at. So that's going to be 2x over e to the 2x. Now if I plug in infinity now, 2 times infinity, e to the infinity, I still have infinity over infinity. Okay, let's do L'Hopital again. Derivative of 2x is 2. Derivative of e to the 2x is e to the 2x times a factor of 2. Okay, so this is going to be the limit as x approaches infinity of 1 over e to the 2x. Now, if I plug in infinity now, I would have 1 over infinity. Now, 1 over infinity is 0. So now I am able to determine the limit. Okay, now the one note to make on this is we're going back to limits. Okay, remember, we're doing limits. This is different than the quotient rule. If I'm doing the derivative of something over something, quotient rule. Quotient rule, how do you spell that? Okay, if you're trying to find the limit of something that is indeterminate, that's we're going to use L'Hope, okay? Not only for limits, not for derivatives.